darker, more dramatic.
Okay, get started. So just a quick overview of the weather. It's going to change over the next few days. So there's this low pressure sitting in the North Atlantic, UK here. Here's the UK. And what this low pressure is doing is wrapping air anti-clockwise around it. So we go forward in time. You'll see the warm air, which is the red colours, and the cold air is the blue colours. The warm air starts to get wrapped around. You see that there? So we've got this stream of warm air which creates a warm front followed by a cold front. So the boundary between the cold air to the east and the warm air further west, that's the warm front. And then the boundary between the warm air and the cold air, that's the cold front. So this is going to bring quite a change to the weather. It's going to become a bit more mild, but also quite damp, obviously. So this warm front first is going to bring a lot of precipitation over the next couple of days, probably Tuesday evening through Wednesday, maybe through Thursday. Okay, and then colder into the weekend. The reason why I've shown you that, so this is quite a common occurrence this time of year, these low pressures in the North Atlantic, but the reason why I've shown you that today is because there's a kind of cloud that we'll be considering today which occurs just ahead of the cold front. So after we've had the warm front and the precipitation associated with the warm front, just ahead of the cold front we get a certain type of cloud which is quite interesting. They're known as altocumulus clouds. Altocumulus. So this is one of those cloud types. It's a thin layer cloud. It can be altocumulus cloud or it can be altostratus. The alto bit's the important bit. It's a thin layer cloud which is super cooled. And I showed you examples of these clouds last lecture, where there was this hole in the cloud where an aircraft had flown through the cloud and nucleated ice in the cloud. So we'll consider more properties of these kinds of clouds today, these altocumulus clouds. Altocumulus or stratus. Altostratus. So those are the clouds we'll be considering today. So let's just have a brief recap. I can't remember what we did last week. So what we found last week, we talked about ice nucleation on Monday, and we talked about how ice crystals grow, and the finding there, this is on Tuesday, the finding there was that the ice crystals, we can describe how ice crystals grow from water vapour in much the same way as we describe how droplets grow from water vapour, by utilising Gauss's law, which seems strange. It's nothing to do with electrostatics, but the equations, the form of the equations is exactly the same. So we can draw analogies between growth from the vapour and the vapour flux lines, and electrostatics and the electric field lines. So the equations are exactly the same form. And so I guess the important point, the reason why we get ice crystals leading to precipitation, is that ice crystals grow faster than liquid drops at the same conditions. That's the first point. And this is because, so I may not have said this, but this is because, mainly this is because ice is the stable phase. But that's a result of the vapour pressure over an ice surface being lower than over a liquid surface. Okay? So it requires, an ice surface requires less water vapour pressure to keep the ice molecules in the solid phase than liquid. So liquid's more likely to evaporate, water molecules are more likely to escape from a liquid surface than they are from an ice surface. That's why the ice crystals grow faster than the droplets. And we also saw that ice crystals have a range of different habits, different shapes, and these habits depend on the supersaturation of water vapour, which is related to how much water vapour there is above saturation. And we don't really know the reasons. That was the main thing you need to take from that. We don't know the reasons why we get these different habits. Okay, and that's still being researched. And so today I want to talk about how we describe, when we've got liquid drops and ice crystals in the same volume, how we describe what happens next. Because this is, if you want to consider an altocumulus cloud or an altostratus where we have some ice nucleation, then we need to think about what's going to happen next if we've got liquid and ice. So ice nucleation's happened. So we'll analyse this by looking at the supersaturation. So we'll look in detail what happens to the supersaturation, and that can tell us quite a bit about how the cloud behaves. Okay, so I might do some derivations today. You don't need to do the derivations. The important bit will be the final equation. So the final equation and how you describe different terms in that final equation. So we'll get onto that shortly. So you've all seen a cloud somewhat like this. It might have been a different example last lecture or on Monday, I can't remember. But it's a high level, or mid-level, sorry, so slightly supercooled altostratus cloud, or altocumulus cloud, because there are different clumps. This is altostratus, this is altocumulus, and in the middle, this is where an aircraft has flown through the cloud and nucleated ice. So that's somewhat an artificial process, but nevertheless it gives a clue into what's going on inside this cloud. So the ice crystals seem to be growing, and they are actually, it's difficult to see, but they're actually evaporating the droplets and starting to precipitate. I think it was more clear in the example last week. Okay, so that's quite interesting. I'm going to show you a video now of me playing around in the lab, and I'm going to show you this process which is called the Bergeron-Thin-Dyson process, and we'll talk about what it means later. So we're in the lab, and this is in a freezer, and so it's cold, and there's supercooled water being nebulized. So there's a cloud here, and there's a torch shining upwards so we can see all the scattering from the supercooled water. And then what I'm going to do next is I'm going to nucleate ice in this cloud, and we'll see what happens. And the way I'm going to nucleate ice is to use a pop. So it's a syringe with a cork on the syringe, and I'm going to compress the air in that syringe and allow the cork to pop off. So that's like an adiabatic expansion. And that's going to cause some cooling, some local cooling, which will nucleate ice in the cloud. So we'll see what happens. So we've got supercooled droplets here, and I've just nucleated ice there by using this pop method. So you can see the droplets are creating a lot of scatter in there, which looks like smoke. And then you can start to see the ice crystals, which are reflecting more light. So they lose the smoke-like appearance because the droplets are evaporating there, and the ice crystals are growing. You can see these specular reflections. Every now and then you see a lot of light being reflected back to the camera. You see that? So the properties of that cloud change quite a lot. That's because the droplets have evaporated and the ice crystals have grown. And the ice crystals look a bit larger than the droplets. There's fewer of them. That's injecting a bit more supercooled cloud. Just blowing more supercooled cloud from the nebulizer into that freezer, into that volume. You see it looks like a liquid cloud again, but because there are ice crystals in there now, eventually the ice crystal eats away at the liquid cloud. So once we've nucleated ice, then the water vapour goes to the stable phase. It takes some time, there's a time scale. That's what's happening. You see that? Okay, good. So this is known as the Bergeron-Findyson process, where ice crystals grow at the expense of the droplets. Actually, some people like to add Wegener as well. So Wegener Bergeron-Findyson process. So what have we got? We've got droplets, we've got ice crystals, we've got water vapour molecules, and the droplets attach to the ice crystals in this situation, and they evaporate from, the vapour molecules attached to the ice crystals, vapour molecules, and the vapour molecules escape from the droplets. So we need to understand how we explain that. Eventually the droplets shrink in size and completely evaporate. Okay, so this is an important process for how rain forms in clouds. So I've talked about ice crystals growing, and we talked about droplets, not the growth of droplets not being fast enough, but the growth of ice crystals is fast enough. If you go back to the 1930s, a paper by Bergeron said this thing: almost every real raindrop and snowflake originate around ice crystal, or snowflakes obviously, but raindrops too. That's when they melt. And also Findyson clouds, which are formed entirely of water particles, cannot produce raindrops, essentially, but they can only produce the small drops of drizzle. So as you'll see, we'll have quite a lot of rain over the next few days, and most of that rain is in the mid-latitudes, will have formed via this process. Oh, I meant to take that slide out, we've seen that one before. So this is looking at the same thing but through a microscope, optical microscope, as a growing ice crystal surrounded by droplets. So we can see in the vicinity of the ice crystal the droplets are evaporating. And these 5 stages are what I've just described on the previous slide. Ice particle enters water cloud, cloud is supersaturated with respect to ice because we have droplets under the saturation vapor pressure over an ice surface is lower. So if we divide the partial pressure by the saturation vapor pressure over ice, it will be supersaturated with respect to ice. What do I mean by that? If we have droplets, then the RH is approximately equal to 1. if we have droplets, and the RH is equal to the vapour pressure divided by the saturation vapour pressure. This is over liquid. Relative humidity over a liquid surface. If we want to calculate the relative humidity over an ice surface, it's a similar equation. It's the vapour pressure divided by the saturation vapour pressure over ice. You'll see this in the PDF of notes. So we want to calculate if we have an RH over liquid equal to 1, then set this equal to 1 E over E. So E equals ES. Okay, and so when I calculate the RH over ice, we'll take ES because it's equal to E and divide by ESI. And I told you on the first slide that the saturation vapour pressure over ice is less than the saturation vapour pressure over liquid. So if that's the case, we must be supersaturated with respect to ice. So that means that the ice crystals are going to grow because we have this supersaturation. Remember, we need supersaturation for ice crystals to grow, to force the vapour molecules towards the ice crystals. And then eventually what happens is we deplete the water vapour to the point where it goes below water saturation. When that happens, the droplets evaporate. Okay, so we've got this situation where the ice crystals are growing and the droplets are evaporating. And we need to explain that. So, just another piece of research which is, it kind of justifies why we need to look at this situation. So, there's a train of satellites which orbit the Earth, which look down and remotely sense the properties of clouds. And from these satellites, we can get the phase of the cloud. We can tell you whether it's droplets or liquid. And we can compare this to the Met Office models. So this is we'll have to think about what this plot means. So this is a Met Office weather forecast, a global forecast over a period of time. And they've taken some statistics from this weather forecast and looked as a function of temperature in the atmosphere. So that's like your vertical coordinate, because temperature decreases as we go up in the atmosphere. So this is approximately your vertical coordinate. Then we can do a histogram of the ice water content. So if you think about at this temperature, we'll take a slice and we'll calculate a histogram. So we'll calculate a histogram of ice water content. Okay, so this is ice water content. This is frequency. That's at every temperature. So there's a most common value, and you see the most common value decreases as the temperature goes up. So the reason for that is the reason why the ice water content, the reason why the mode decreases as the temperature goes up, down even, the reason why, say that again, the reason why the ice water content goes down as the temperature goes down, you might expect the opposite, but that's because of the saturation vapour pressure. If you think about the saturation vapour pressure, so the amount of water vapour that the air can hold decreases as the temperature decreases, and because of that, the amount that we can condense out of the air also decreases with height. So this makes sense, kind of, and there's a spread to the distribution. But when we look at the observations, we see it's somewhat different. So we see from the observations we're more likely to have lower values of ice water content. at higher temperatures. So it's completely different to the weather forecast models. Okay, so we've got this completely different situation. When we look at observations, global observations from the satellite is different to the weather forecast models. So the weather forecast models struggle to get this process right. They struggle to represent the Berger-Impin Dyson process. They just can't do it. And this is a current problem. Okay, so people are working on this problem right now to try and solve it. And there's been a lot of progress in the last few years on how to fix this problem. So I'm going to skip to the visualizer to talk through some derivation. How do I go? Let's think about how we represent these altocumulus clouds now. Visualizer. So I'm probably not, I won't have time to go through the full derivation. So the question is, what affects the supersaturation S subscript L in clouds? And the reason behind this, the reason why I'm focusing on supersaturation is because A, it's one variable. So, when I think about clouds, I can think about however many variables I want to think about. But supersaturation is just one variable, which simplifies the analysis. And if I can describe the supersaturation in clouds, then I can describe whether liquid's going to grow, or whether ice is going to grow, or whether liquid's going to evaporate, or ice is going to evaporate. So this one variable can tell me quite a lot. That's the motivation behind why I'm looking at supersaturation. So the supersaturation, we know, you've seen this before, that the supersaturation is equal to the saturation ratio minus 1, which is equal to the vapor pressure minus the saturation vapor pressure divided by the saturation vapor pressure, because small SL is equal to E over ES. It's the same as the RH. The saturation ratio is the same as the relative humidity. People go between these two variables. They use either RH or S. Doesn't matter which one you choose. So we can differentiate this with respect to time, and so write that down. So we get dSL by dt. So I can do this using the quotient rule for differentiation. You end up with something that looks a bit like this. That's equation 1. And we also know that the mixing ratio of water vapour, W subscript V, is this constant epsilon, which is ratio of specific gas constants, times the vapour pressure divided by the total pressure. So I can rearrange that for E quite easily and differentiate again. So again, this is quotient rule. I should have said, so E equals WVP over epsilon. So that's quotient rule again. So all I've done is look at the rate of change of supersaturation and what it depends on. And the derivation now is trying to find the terms on the right hand side, these things on the right hand side, in terms of things that are I can easily calculate, I can easily understand, and substitute them into equation 1. So I don't want to go through the full derivation, but if you're interested, that's in the PDF of notes. The important points are that if we look at, say, the rate of change of water vapour, then we can explain the rate of change of water vapour in a parcel of air as being due to the rate of change of, because water is conserved, the rate of change of liquid water and the rate of change of ice water. So two terms. So if water goes down, then either liquid water must go up or ice water must go up. You see what I mean? Because the total is conserved. And so the important points are that the rate of change of the liquid water content for liquid drops, dm by dt, is proportional to the radius of the drops, the average radius of the drops, the first moment of the distribution, times the supersaturation of a liquid. And so the rate of change of the water vapor of the liquid water mixing ratio, W subscript L by dt, is equal to, and it will be however many droplets I have, we'll call it N liquid, the number concentration, times dm by dt. And we'll assume that we're not considering changes in number of drops, we're just considering the change in the average drop mass. And then for ice crystals, and we derived the growth of drops from the vapour using the Maxwellian growth theory a few lectures ago. For ice crystals we derived the similar thing last lecture, and so the rate of change of ice crystal mass M, was proportional to, and it was the capacitance, the electrostatic capacitance, C bar, so the average, multiplied by the supersaturation over ice. So we calculated that using the analogy with Gauss's law last lecture. So these are the important points, but S subscript I can be calculated in terms of the supersaturation of a liquid. How do I do that? Well, S subscript I plus 1, that's the saturation ratio over ice. So that's equal to vapor pressure, water vapor pressure divided by the saturation vapor pressure over an ice surface. Okay, so if I multiply Si plus 1 by the saturation vapor pressure over ice, which is just a function, ESI T. Now this whole thing is E, that's the vapor pressure, and then if I divide by ES, this is now the saturation vapor pressure over liquid, saturation ratio over liquid, and and minus 1, that would equal S subscript L. So all I've done there is calculated the saturation ratio over ice, Si plus 1, multiplied by this denominator to get E, and divided by ES. Now that would be the saturation ratio over liquid, and then subtract 1 to get the supersaturation over liquid. So I can describe this, I can describe the growth rate of an ice crystal in terms of the supersaturation over liquid. Just need to rearrange. So that reduces the number of variables that I need to think about. And the final result then is what I want to write down. When you do that, you get an equation which looks like this. So the rate of change of supersaturation over liquid in a cloud, and it has 3 terms. Call it alpha, minus beta times dWL by dt minus delta, I guess, times dW ice by dt. Okay, so we've got a few different terms. The first term is like a source of supersaturation. We'll think about what that means in a minute. So the first term, if the first term is positive, supersaturation increases. Well, it's like a source term, as long as the first term is greater than the second and third terms. Second term is related to the growth rate of liquid. So if we have some condensation, the supersaturation is going to go down. Makes sense? And if we have some ice crystal growth, again, the supersaturation is going to go down. And this is just because the total water in a parcel of air is conserved. So we'll go back to the slides. So the equation looks like that. So rate of change of supersaturation in a cloud, and it turns out that this first term here has the vertical wind in it. So if we have no condensation and no deposition onto ice, and there's a positive vertical wind, and the supersaturation will increase. Why is that? So that should make sense to you, because what's happening, it's like the cloud chamber without any particles. What's happening is the pressure's going down as we go up through the atmosphere, so the temperature goes down, so the amount of water vapour that the air can hold also goes down, which means if the amount of water vapour that the air can hold goes down, this denominator goes down, so the relative humidity of the supersaturation goes up. Make sense? So this is like a source, and it's due to, what you need to know is it's due to the expansion and therefore the cooling of the air parcel. You'll need to be able to explain what each of these terms mean. Second term. So this is a little bit tricky. So yeah, in some ways it's fairly straightforward. So we've got the rate of change of liquid water mixing ratio. Okay? And it's negative. So if liquid water increases, the supersaturation goes down. But there's 2 effects. You can see this term in the bracket, there's 2 effects in here. So let's think about what this means. So the first effect is I've got my parcel, total water vapour, liquid and ice is conserved in this parcel. If they add them all up, it doesn't change. There's no sources or sinks inside the parcel itself of the total water substance, the total mass of water. Add up the water vapour, liquid water and ice, it stays constant. Okay? You see there's two terms here. If we have some condensation, then the liquid water increases and the water vapour decreases. That's fairly straightforward. So you might imagine that the supersaturation is going to go down. Does that make sense? Supersaturation is related to how much water vapour there is. Well, there's another term too. So if I have some condensation, the supersaturation goes down as well. So these two terms are both negative, the minus sign in front of them. What do you think that might be? So the first term is just because we're moving water vapour onto the liquid, so the amount of water vapour is going to go down. What's the other term? What do you think the other term might be? That's going to cause a decrease in the supersaturation.
The change of separate vapor pressure due to temperature.
No. Oh,
That's
kind of. No, you are right. But why? Why does the temperature change? You said it, latent heat. So we have some condensation, water vapour condenses onto the liquid, the temperature is going to change. It's going to increase. And the saturation vapour pressure, remember, looks something like this. So this is, let's see, this is temperature, this is high, this is low. Saturation vapour pressure looks something like this. So if we condense water, we go to here. When we divide by ES, the supersaturation now goes down. You see that? Just because we've moved to a higher temperature parcel. So there's two terms there. Same for the ice. Exactly the same for the ice. So we've got constant total mass. Then this term just means that conservation of total mass, supersaturation is going to go down. This term is to do with the latent heat. Same sort of thing. So that's what I need you to, what you need to know for the exam. You need to know what each of those terms are. And now we're going to take a closer look and try and start to analyse this equation. But first of all, I want to show you some examples, just to show you that I'm not telling porkies. So this is an altocumulus cloud, and rather than looking down with the satellite, these are observations from Chilbolton in Middle England of LiDAR. So it's looking up from the surface, laser looking up and looking at the reflected light. So what this shows as a function of time is the kind of reflectivity at different levels in the atmosphere. And what you tend to see in these altocumulus clouds are areas where we have a large backscatter coefficient. So this is where there's lots of backscatter of laser radiation, lots of scattering back of the laser radiation that we're sending into the atmosphere from this height. And what it shows is that at the top of the cloud you tend to get a lot of scattering, a lot of backscattering back to the surface. And what this is supercooled cloud. So the interesting thing with these layer clouds, and you see this a lot, is that supercooled water at the top of the cloud, it lasts for a long period of time. Okay? So at the same time, we can observe with the cloud radar, we can look up and we can see the ice crystals falling out of the cloud. The cloud radar sensitive to the larger particles. So you can see ice particles are here. With the LiDAR is sensitive to the smaller particles. And the interesting thing, like I say, is that these supercooled cloud layers last for a long period of time. So they're known as persistent liquid water at the tops of altocumulus, and it's very important radiatively because it's much more reflective. Much more of the solar radiation gets reflected back to space. And the liquid waters, the red areas on the LiDAR, why doesn't the cloud glaciate? So the example that showed you, the video that showed you, showed if you have ice, it should glaciate fairly quickly, but it doesn't. And this is why the weather forecast models get this histogram wrong. So go back to the histogram just to show you that. The models predict that we have more ice. Have more ice, you have less liquid. That's a fact. The observations show we have less ice and more opportunities for liquid clouds. Why is this? Why do they get it so wrong? It's due to the turbulent motions. And weather forecast models are at a scale, so the size of their grid that they compute the solutions on is too coarse to be able to predict the vertical motions in the clouds. So the cloud scale vertical motions, weather forecast models can't predict these. They're just not powerful enough to be able to hold, to be able to have a resolution that's high enough to be able to resolve this liquid water in the cloud. So there's a paper that talks about this. You can think about a situation where you have a very basic overturning assumption. So a parcel of air goes up and then comes down. And if the time scale required for the parcel of air to enter the mixed phase region, liquid and ice, is short enough, then what will happen is the liquid won't have time to completely evaporate. So it'll evaporate when it's in the downdraft. That happens quite quick. But in the vertical part of the parcel motion, if we go back to the equation, you see you've got this source term. If this source term's high enough, we can have supersaturation over liquid water. Okay? So that's the reason. And now weather forecast models are starting to use this equation to describe where it should be supercooled. And it seems to do a pretty good job actually. I'll show you some examples tomorrow. So just want to extend this a little bit. So we can think about glaciation time scale when we look at the equation for the supersaturation. We can think about glaciation time scale. So I want you to be able to look at that equation and think about a glaciation time scale. Okay, so, and I'll talk more about how you do that tomorrow. But essentially, if you think about three situations, and we look at the saturation ratio. So if we think about having different numbers of ice crystals, so this is a 0.1 per milligram of air. Think about a milligram of air. 0.1 ice crystals for every milligram of air, 1 per milligram of air, and 10 per milligram of air. So as you can see, the fewer of the ice crystals you have, the longer the glaciation time scale. So in the case of 0.1 per milligram, which is about 100 per litre, glaciation time scale is approximately 2 hours. Obviously the cloud in the example lasts for 8 hours. Actually these altocumulus clouds stay supercooled, they can stay supercooled for 24 hours. They're just constantly supercooled. 1 per milligram, you're looking at, what is that? That's about 30 minutes. And then 10 per milligram, what's that, about 5 minutes, something like that, less than 5 minutes maybe. Okay, so think about glaciation time scale. I'm not going to calculate it this lecture, we'll calculate it next lecture. And then motion in the vertical. So that was a stable cloud. This was the situation where the vertical wind is 0. So the source term's 0. So you start with some liquid water, and eventually that liquid water evaporates and supersaturation comes down. At this value here, we're at ice saturation, so the conditions are completely stable. Ice is not going to grow, liquid's not going to grow. It's just condensed to the point of equilibrium. Now a situation with a vertical wind. So we've got a constant vertical wind in the parcel here, and I'm plotting the supersaturation on the x-axis against height on the y-axis. So let's look at what we mean. So this dashed line now is the value of the supersaturation of the liquid water for conditions of ice saturation. So if you're at these conditions, ice will not grow or evaporate, it will stay there. They're conditions of ice saturation. Now let's look at different values. So I think it's a 1 metre per second updraft. So the air is moving up at 1 metres per second. So we've got 0.1 per milligram of ice crystals now. And if we start that simulation off and go up in the atmosphere, you see what happens is the supersaturation increases at first and then starts to decrease. And we've got 1 per milligram. Supersaturation decreases, sits above ice saturation. 10 per milligram, supersaturation decreases faster, sits just above ice saturation. So we've got some questions, just to check that we've understood that. So I'd like you to explain what's going on. So why does the supersaturation of a liquid, in the case with 0.1 per milligram of ice crystals, why does it increase and then decrease? Can you think about why that might happen? We should go back to the equation, maybe. So this supersaturation increases and then decreases. It stays above 1. Okay, so this is a constant term. Why does it increase and then decrease? Anyone want to say? Not sure. So the increase, what's the only positive term? The updraft term. So at the start of the simulation, the updraft term is greater than the two other terms. Greater than the sum of the two other terms. So that's why it increases. Let's break it down. For S to increase, this term needs to be greater than these two other terms. For S to decrease, these two terms, the sum of these two terms, needs to be greater than the first term. Does that make sense? So why am I, what's changing then? Well, think about if we have supersaturation over liquid, and we do, because it's greater than 0, SL is greater than 0, then what can grow? What phase of cloud can grow? Can the liquid grow? Can the liquid droplets grow? Can the ice grow? What do you think? Yes or no? Can the liquid grow? 50-50, can it grow? I'm going to stay here. Yes or no, can it grow? Supersaturation of a liquid is greater than 0. Can it grow? Can ice grow? If we're supersaturated with respect to liquid, we must be supersaturated with respect to ice, as long as the temperature's below 0. Because remember at the start of the lecture I said the saturation vapor pressure, the pressure required to keep ice crystals, to keep water vapor molecules in the ice is less than to keep water molecules in liquid. That means that the saturation vapor pressure over ice is going to be is always going to be greater than over liquid. So both the liquid and the ice are going to grow in the first example. So both the liquid and the ice are going to grow, so these are going to be positive. And eventually, if you think about what I said at the start, I said growth rate of a single droplet is proportional to the size and the supersaturation. So supersaturation is greater than 0, so this is positive. But the size, it then increases, then the size of the droplets also increases. So that means as time goes on, dWL by dt is going to increase because the size of the particles is going to increase. Same for the ice, dWi by dt. So those terms are going to get greater as time goes on, and they're going to compete with the first term. So that's why supersaturation increases and then decreases in that case. Do you think you could explain that? If I asked you that in an exam, do you think you'd be able to explain it? Hint, hint, it might be on the exam. Okay, so in the other two terms, at this point, the number of ice crystals is so great